Hello, my name is Bohua Li. I'm a postdoc at Tsinghua University. I will talk about the linear polarization signal of the 21 centimeter line from the Epoch of Reionization, addressing questions including what are the dominant sources of the polarization signal from the EOR, what does the signal look like, and how likely it is to be detected by the upcoming SKA telescope. This work is done in collaboration with Yi Mao and his former student. Please check out our newly submitted paper on arXiv. First, we would like to remind everyone that the 21 centimeter radiation from the EOR is polarized, and most of the major radial interferometers are sensitive to the full polarization information described by the Stokes parameters. Therefore, it is reasonable to consider not only the 21 centimeter brightness temperature, that is, the Stokes I, but also consider polarization as well, namely Stokes Q, U, and V. They may provide complement information to the brightness temperature. Current and future instruments which have low-frequency receivers targeting at the EOR and can measure polarization include LOFAR, MWA, and of course, the Phase 1 SKA Loeb telescope. Babbage and Loeb in 2005 pioneered the study in a 21 centimeter polarization signal from the EOR. They classified the production mechanisms of 21 centimeter polarization into the intrinsic mechanisms, meaning that the 21 centimeter photons are created with polarization, and the secondary mechanisms, meaning that the original emissions are unpolarized but obtain polarization later in transfer. I will not discuss all the mechanisms in detail, but just state that the dominant polarization signal from the epoch of reionization is produced by Thomson scattering of free electrons, as highlighted here. It generates linearly polarized signal Q and U, and by symmetry argument, only E-mode polarization is generated by scalar perturbations, the same as the CMB. Besides production mechanisms, there are also propagation effects which can convert E-mode polarization into B-mode. For 21 centimeter radiation, Faraday rotation turns out to be a substantial effect which distorts the signal and poses challenges to observation. In this work, we do not calculate the effect from Faraday rotation, but focus on a better modeling of the signal itself, producing realistic predictions which improve upon the early results. We calculate the angular power spectrum of the E-mode autocorrelation and its cross-correlation with the brightness temperature. Same as the 21 centimeter temperature power spectrum, there are two major sources for the signal: the neutral hydrogen density field and the redshift space distortion effect. We derive the expression by standard procedures. This is the only slide in my talk that contains equations. In the expression for the EE power spectrum, where all the P's of K are the power spectrum at emission, and the T's of K are the transfer functions. In their expressions below, G of eta is the visibility functions, which depends on the global ionization history. Therefore, our goal is to model the fluctuations of the patchy reionization process as well as global history. To do this, we use semi-numerical simulations by 21 centimeter fast. We applied two box sizes to achieve the required K coverage and variate the reionization model parameters to see the effect of different ionization histories on the polarization signal. All the three models satisfy the current observational constraints. Here are the results. In this plot, we compare the relevant power spectra that sources the 21 centimeter polarization to those used in the previous work. In their paper, they used a toy model for reionization, which produces a neutral fraction power spectrum that is flat on large scale and drops exponentially on scales below the typical bubble size. We have different results from our realistic modeling, shown by colored curves. And we also include two additional terms that are non-negligible when the fluctuations in the neutral fraction is nonlinear. As a result, the polarization power spectrum from our calculation, both EE and TE, shows that their amplitudes are smaller on superbubble scales and larger on subbubble scales than previous results. On small scales, our simulation results have contributions from partially ionized bubbles. On large scales, our model assumes a scale-independent H1 bias, shown in the right-hand side figure. It is in contrast to the H1 bias from the toy model, which has a red tilt. Because of this difference in the large-scale H1 bias, our TE power spectrum shows a flip of sign at L about 50, indicated by the purple dashed dotted curve. We also study the evolution of the polarization power spectrum during the Epoch of Reionization. For any given angular scale, the evolution of the amplitude is certainly different for different ionization histories when plotted against redshift. However, in the lower panel, when plotted against the global ionized fraction or the H1 volume filling fraction, we see a converged trend, regardless of the reionization model. This robust mapping between the polarization power and the global ionization fraction may allow us to probe the global history of reionization by 21 centimeter polarization power spectrum. Finally, we would like to see the detection prospect of this signal by the SKA-1 low telescope. Without concern with foregrounds, we find that the thermal noise alone from the design sensitivity of SKA-1 low, indicated by the black dashed line in the figure, does not support the measurement of the 21 centimeter polarization signal within reasonable integration time, as opposed to the previous claim of detection within 1 month of SKA observation time. And besides the noise, there are several systematic effects which can challenge the measurement, and Faraday rotation is the largest among them. In conclusion, we have made by far the most realistic prediction of the 21 centimeter polarization signal from the EOR, and demonstrated some of its features which encode valuable information on reionization and large-scale structure. However, the strength of this signal is too weak to be seen by SKA-1 low. The first detection of the 21 centimeter polarization signal might come from the cross correlation with another tracer of the EOR, once we know how to treat all the systematics. Thanks for listening to my talk. Any questions or comments are welcome.